Introduction to galaxies. The universe contains billions of galaxies, each with billions of stars. Galaxies are massive systems that are held by gravity, consisting of stars, gas, dust, and dark matter. Understanding galaxies help us learn about the universe's origin, structure, and evolution. Okay, so galaxies are. We also live in a galaxy, and it's called the Milky Way. And these are group of massive systems that are held by gravity. They contain billions and billions of stars, which are held by gravity and dark matter. And galaxies also played a crucial role in discovering dark matter, because many physicists, there's a physicist named Fritz Zwicker, who discovered that galaxies are like the outer parts of the galaxies and the inner parts of the galaxies are moving at the same speed. And uh, but our normal classical physics says that this should not be the case. And they also observed that the galaxy does not have enough mass to be held by gravity, which means that they should be flown off and there should be no galaxies. But the thing is that the galaxies are there and we see them, so it means that there are dark, and there's something that we cannot observe but has massive amounts of gravity. That is how we discovered dark matter, and we discovered that it would be about 10 times more heavier than the normal matter of the galaxies, and uh, they should be centered at the uh, center of the galaxies. But what we have discovered right now is that it has a uniform distribution, which physicists are still trying to explain. The Milky Way galaxy overview. So, the Milky Way is a home galaxy, a spiral galaxy approximately 100,000 light years across. It contains 200 billion stars, along with gas, dust, and dark matter. Our solar system resides about 27,000 light years from the galactic center within one of its spiral arms. And the numbers are these the numbers like the 200 billion stars and 100,000 light years. These are all approximations. Uh, so, so as you can see in the picture, this is a picture of the Milky Way. Uh, like to take a picture of something, we need to get across it, but we have just approximated what our galaxies would look like by observing other galaxies. We see that there's a central bulge, there's a disk, and an halo. Galaxy formation theories. A galaxy is likely formed from small fluctuations in the early universe's matter uh, distributions. Over time, these fluctuations grew via gravitational attraction, leading to galaxy formation. Various models include hierarchical, emerging, and monolithic collapse to explain galaxy assembly. So, what we first think how a galaxy form it would be formed is that there would have been a large ball of gas and dust, and that would have been attracted by dark matter halos. So these would have been attracted by dark matter, and what happens is that whenever something starts to rotate, it starts to flatten out, and that could have caused the star formation. As you can see in the picture, is clearly given that dark matter attracts many gases, and the ball of gas starts to rotate and flatten itself, and the motion created by the spinning disk causes the spiral arms of the galaxy to form and start rotating with it. hierarchical clustering. The Milky Way formed 13.6 billion years ago when dark matter gravity pulled in primordial gas. This gas created the first stars, creating a dense central bulge. Rotational forces eventually flattened the remaining gas into a spinning spiral disk where galactic collisions and ongoing starbursts shape the galaxy we see today. Okay, so it's the same thing that I've explained is that smaller and smaller objects collide and form bigger objects. So it says that because of dark matter, a lot of gas got pulled in a space, and what happens is that when it started rotating, and made that flattened it and causing the arms the to form and start rotating. So, ladies and gentlemen, do you have any questions?
Nothing as of now.
Okay. Some new people have also joined, so thank you for joining us. And if you have any questions, you can ask us. And how do we find galaxies? Astronomers use telescopes across the electromagnetic spectrum to detect galaxies. Optical telescopes reveal the visible light emitted by stars and gas within galaxies. Radio, infrared, and X-ray telescopes help observe regions obscured by dust or emitting non-visible radiation. So what does this say is that whenever we find a lot of radiation, like a different range of radiation coming from a particular place, like a galaxy, like all types of radiation, we can find out that it is a galaxy, and by under spectrography. So spectrography. So whenever something emits, when an atom absorbs a photon, what happens is that the electron in the lower orbital goes to a higher orbital and it emits a photon, and then the electron goes to the uh, lower orbital and then emits a photon, and then it releases a photon, which would be the exact energy difference between the higher orbital and the lower orbital. So it gets uh, reflected, and that's okay. You have a question?
So like I was wondering the accuracy of what you just said. So like what actually happens is that when in an atom a photon hits an electron in a lower orbital, it absorbs that photon and goes to a higher energy shell.
Yeah.
And after a while, it releases that photon and goes back to the original shell. It
Yes.
doesn't emit photon in both cases. It absorbs in one and emits in one.
Okay, what it does is that the electron in the lower orbital, after absorbing that specific photon, it goes to a higher energy level or orbital, and after some time, what happens? It falls back to the lower orbital, and then it emits that photon, and that photon's energy level would be equal to the energy difference between the higher and the lower orbital. So, do you understand it? Hello, Sarvesh. Okay.
Yes. And fun fact, this is also why glass lets light pass through. The energy of the photon is not enough to move the electron from lower orbital to higher orbital, and that's why the photon does not get absorbed. But if you have very high energy photons like UV and all, it does get absorbed, and that's why UV can't pass through light through glass. Fun fact.
Okay. So, there's another question. How do we know a faint smudge of light is a whole galaxy rather than just a nearby star? Uh, if like there are many ways we can use spectrography or the redshift. Uh, like in spectrography, what happens is that there are few. If we look at a spectrography chart, graph? that there are few black lines in it, and the black lines are caused by the absorbing and re-emitting of these photons of that specific region that was blacked out, which was gone from the graph. So it helps us find the composition of that specific thing that we are trying to observe. And the redshift, uh, okay, we'll just talk about the redshift later on. So multi-wavelength detection. Okay, so multi-wavelength detection finds galaxies by capturing light invisible to human eyes across the electromagnetic spectrum. Infrared telescopes pierce cosmic dust to reveal hidden or ancient highly redshifted galaxies. Meanwhile, radio telescopes map cold stars forming gases, and X-ray observatories pinpoint high energy phenomena like active feeding supermassive black holes at galactic cores. Okay, so there are many telescopes at NASA uh, that detect uh, radiation in different spectrums like X-rays, gamma rays, infrared, and microwaves. So and by that we can uh, like gamma rays and X-rays, we use that to find objects or energetic events like supernovas or other things. And and infrared also reveals highly redshifted galaxies, or you can say the galaxies that are moving farther and farther away from us because due to the universe's expansion. So Aryan, you have also joined. Hello Aryan, are you here?
Hello, yes, Arjun.
So right today we are discussing about galaxies, how are they formed, and what is uh, how do we find them, and how do we measure their distances. Okay, so infrared uh, with infrared telescopes we can see highly red-shifted galaxies, the galaxies which are moving farther and farther away from us. And I think so there was some I can't just remember, there's a galaxy that that's the farthest away from us, or what we suspect is the highly redshifted galaxy. I just can't remember its name. And so what happens is that this galaxy detecting is also very okay. How does dark matter influence? There's a question there. How does dark matter influence galaxy detection? Okay, uh, in detecting them, I don't think so. It causes a problem. Uh, the the dark matter does not interact with the photons that we see. Uh, they only have the gravitational effect on us. So it's like air. We cannot see it, but we know that it's there. We can feel it. So we just feel its gravitational effects, and the only problem that it may create, or the only thing that it can do with its gravity is maybe gravitational lensing. If there's a lot of matter, uh, dark matter in a spot, what happens is that it will bend the rays. This is called gravitational lensing, and this is why we can see we can see the same galaxies at different angles, and many of them at the same time. Observing the universe with telescopes. Okay, you have raised your hand.
Can I like add another fun fact?
Okay,
Like, can you go to the previous slide?
yes.
If you look at the molecular hydrogen image and the optical image, you will notice that the places where you see hydrogen align perfectly with the dark regions in the optical image. So, like, we know that the hydrogen is absorbing the like visible light, and that's why we see the dark regions. This is like primarily why we do imaging in different wavelengths.
Yes, I didn't notice that one. The so the hydrogen lines, right?
Yeah, yeah,
Okay.
yeah, it's fine.
Observing the universe with telescopes. Ground based telescopes are equipped with advanced cameras to capture deep sky images. Space telescopes like Hubble avoid atmospheric distortions, providing clearer images. These instruments allow us to detect distant galaxies billions of light years away. So, that is how we detect galaxies. I don't remember how many spectrums can the Hubble see, but I know two of them. I think so. It was X-ray and infrared. So uh, these telescopes are not on on the atmosphere because there are distortions, pollution, and other factors. That's why it's in low Earth orbit, which provides clearer images and less disturbances. And this galaxy detection stuff is very hard because most of the light coming to us gets absorbed and re-emitted, so it may not reach us. So, like in tens of millions of photons, only few of them can reach us because of the gas and dust present in between. So, Aryan, are you understanding the concept? Hello, Aryan.
Hello, Aryan.
Did you understand this concept?
No, my speaker is not working properly.
Oh, you can't hear me properly. Okay. You can try to rejoin. So, ladies and gentlemen, do you have any questions?
No, there is a problem inside my device.
Okay. So I think so. You can just write your questions down then. Measuring galaxy distances. Redshift measurements are crucial in estimating how far away galaxies are. As the universe expands, light from distant galaxies stretch to longer, redder wavelengths. The greater the redshift, the farther and older the galaxy is in cosmic history. So, one thing is that if I have some hydrogen, let's say, in a rest position, and if I measure its spectrograph, and if I do spectrography of that, I know that in that specific region that is lost, it means it's hydrogen. So, and if I look at a galaxy which contains a lot of hydrogen, which is moving away from us uh, due to the expansion of space, there would be an redshift. It would be perfectly redshifted by that amount it's moving, and by that we can just minus the original rest position and the observed position, and then we'll get an value. And if we just plug in that value in some, there are few equations, we'll get its approximate distance of that galaxy. So we what we did is that we took the rest position of that, the spectrography of that hydrogen at rest position, and then we looked at other galaxies which contain hydrogen. And what happens is that the bar shifts perfectly, and when we uh, just subtract them, we'll get a value, and by plugging that value in equations, we'll get it approximate distance. So, Saksham, you've also joined. Hello, Saksham. Hello, Saksham, are you here? Okay. So, Saksham, do you know about type 1 supernova? Hello, Saksham. Okay, I don't think so. So, Aryan, do you know about Type 1A supernova? Do you remember it, Saksham and Aryan? Okay, Sarvesh, do you know about it?
Um, is it like a white dwarf takes matter and something like that? I honestly don't remember, but like I've heard it.
Yep,
And
yep.
then it reaches a Chandrasekhar limit, and then carbon fuses, and boom, something like that.
Yes. So, do you, so can they? Do you think that they can help us in the galaxy distances?
Probably.
Okay. How did that? Okay. So how's the how would that help? How would the supernova help us?
Um, you could measure the redshift of the supernova or something. I honestly don't know this one.
Okay. If I wanted to get the redshift of that supernova, if I could do that, why couldn't I just do it with the galaxy itself? Okay. So, Saksham, I think so. I think so. We have heard of this question before. So, Saksham, my question is, how do super Type 1A supernova help us figuring out galaxy distances?
Yes, Aryan, please repeat your question.
My question is that how do Type 1A supernova help us figure out galaxy distances?
They can they can figure out galaxy distances by their emitted light.
Can you repeat?
By their emitted light. If they are, suppose there is
If
a supernova occurring in Andromeda galaxy and it is a type 1A supernova. So scientists will use its emitted light to find out the distance of the galaxy.
okay, if I so it means you are saying that we have to by light we can do that, right? By observing that light.
Yes, Aryan. Not only by light but redshift and blue shift events.
Okay. So you have raised your hand. Do you want to say something?
Um, I think I might know. I know for a fact that they have consistent brightness. So like
Okay,
if they go farther and farther away, their brightness dims, something like that.
yes, you got it.
I'm not sure.
So, uh,
Yeah.
and type 1A supernova, what happens that the white dwarf does breaks that Chandrasekhar limit of 1.44 solar masses. So then it goes a supernova, and that supernova is like that brightness is pretty consistent. So by using the inverse square law of light, so that light's intensity gets weaker with distance. If we just do that, we'll get its distance. So that is how these type 1A supernova help us figure out the distances between stars. So Saksham, did you get it? How do we use them to find out distances?
Yes, Aryan.
Okay. Measuring galaxy distances. Astronomers measure galaxy distances using the cosmic distance ladder. They track pulsating Cepheid stars for nearby galaxies and look for type 1A supernova, which expose with uniform peak brightness. For more distant one, for deep space, they measure cosmic expansion redshift. Faster receding galaxies sit farther away from us. So, uh, does anyone here know what is a Cepheid star?
Yes, Aryan. Can I explain it to you?
Okay.
A Cepheid. Okay, so a Cepheid star is a type of a star. Vision changes its brightness over a period of time. Means it pulses its brightness. It was first discovered by Henrietta Leavitt and was detailed and was studied in great detail by scientist Edward Jenner.
Edward, okay. So how are they pulsating? Do you know how their pulsating helps us?
So, so again, first you have to tell that why do they pulsate?
Okay.
Means what happens in them so they pulsate.
Yep. Do you know about their pulsating stuff?
I know, but do you know about it?
Yep.
So what is it? Can you explain to me?
Okay. You should go first. I know what I'm asking. Okay.
So you must know that as the hydrogen in the star increases, the brightness of the star increases, and as the helium is increased in the star's core, the brightness suddenly dims. Do you know about it?
Yes.
So this is
Okay.
what is
So
happening to these little stars. As the helium is increased in them, their brightness starts to dim. And when the hydrogen is increased, their brightness again reappears, which helps their brightness to do pulsation. And this pulsation will help to find out the distance.
okay. So how does that help us figure out distances? How do these pulsating stars help us figure out the distances between galaxies?
Or their pulsating frequency and pulsation time period.
Okay. So what happens is that the reason they're fluctuating is because of the hydrogen in their outermost helium in the outermost layers. What happens is that they get ionized, and what happens is that they become opaque. So they become like a valve, a pressure cooker, you can say. And what happens is that it starts to expand because the light cannot escape. It has become opaque, and the light cannot expand, cannot escape. And what happens is that it gets bigger and bigger. And what happens is that after some time, what happens is it cools down and returns to its original position. So that is that is how it's pulsating. And uh, and their pulsating are related to its other properties like mass and luminosity, and these are mostly yellow or orange dwarf stars. I don't remember. So they are 4 to 20 times massive and 100,000 times luminous than our sun. And if we okay, so Saksham, do you wanted to say something? Your voice is not coming properly. Hello, Saksham, your voice was not coming properly. Can you just rejoin? Okay, so I someone else has also raised their hand.
Yeah, that's me.
What's the question?
So my question is about the galaxy detection.
Okay,
So as we see in nowadays, artificial intelligence is picking the culture. So what is the role of artificial intelligence in play galaxy detection?
okay. In galaxy detection, what the thing that I can, uh, the only thing that I can, I that might take place is that we can use AI uh, to make use of these sapphire stars to make to know their to measure their pulsating periods. And by that by plugging it in equations and stuff, we'll get its usual brightness, original brightness. And the brightness that we are getting, if we use the inverse square law, we'll get its the distance. So that's the only thing I can think of right now. And uh, Maybe they can be used for detecting uh, energetic events like certain irregularities in the galaxy, so they may be helpful in that area, or the things that are repetitive or something. So maybe like the AI could detect and get a spectrograph of a certain galaxy and tell its elements by this graph. So these are the things that AI can or maybe take uh, or help us in. So did you get? Are you satisfied?
Okay.
Okay.
Yeah, definitely.
Okay. So hello, Saksham. What I think so. You were trying to say something, right?
Yes, Aryan.
Yes. Yeah. Could you just say that right now?
Just as you said that these superstars pulsate because of their hydrogen and helium inequalities. Like when the hydrogen increases, as you know, the brightness of the star decreases a bit, and as it becomes smaller, its brightness increases. This is what happens in the secret stars.
Are you saying that helium and hydrogen are doing that?
Yes, your
I think.
aesthetic their inequalities are helping. Like when the helium increases, the brightness decreases.
Okay. Okay. So can all of you just think of another way of detecting a galaxy's age by spectrography? Hello, Saksham. Can we tell an galaxy's age by looking at its spectrograph? Saksham,
Yes, are you?
can we say the age of a galaxy by its spectrograph? I think so. We have done that topic before in our presentations.
I don't know, are you? I don't remember, but I think it is possible.
Your voice was not coming properly. Can you just rejoin again? Okay, so Sarvesh, can you think of a way to determine a galaxy's age by looking at its uh, spectrograph? Hello, Sarvesh.
I'm not sure. I'm not sure.
Okay, so have you heard a section? Were you trying to say something?
Aryan, am I audible to you?
Yes. Yes.
Okay, Aryan.
So, what were you saying about that question? You don't know. Okay. So, Sarvesh, have you heard what metallicity? Have you heard the term metallicity?
No.
Okay,
Could you
so
explain?
metallicity is the amount of like the metallicity of a star. It tracks the heavier elements of a star. So, can that help us determine the galaxy's age? What do you think, Sarvesh?
Could you repeat it? I just had some technical issues. Could you repeat it?
Metallicity is the track of heavier elements in something. So can that help us figure out something's age?
Oh, I'm not sure. This is the first time I'm hearing about it.
Okay. So Saksham and Aaron, do you guys have any guesses or answers? Okay, I don't think so. So should I answer it, Saksham? Okay, I'll just answer it. So the earliest stars were made up of hydrogen, mostly hydrogen and then helium. And if they died, what happens is that they release higher elements, heavier elements into the composition of the universe. And if a galaxy is new, what happens is the amount of heavier elements is higher, and if it's pretty old, the amount of heavier elements would be less than the young galaxy. So that is how metallicity can help us figure out a galaxy's age. So it just provides an as a rough estimation of how old the galaxy can be. Okay, Shant, you have to leave. So we also upload these sessions on YouTube. You can also watch that if you just missed the presentation. So the picture there is the pulsating period of a real uh, Cepheid star, and so these Cepheid stars help us figure out the distances between large galaxies, and their pulsating periods help us figure out its related to their luminosity, and the luminosity what we observe, we can just use that and use the inverse square law of light to figure out the distances between galaxies. Redshift and spectrography. Spectrography analyzes the light spectrum from galaxies to determine their redshift by measuring certain specific spectral lines. Astronomers can calculate galaxies' velocity and distances. This technique helps map the larger scale of the universe, and as I mentioned before, that if we look at its spectrograph and take an element spectro, uh, the hidden lines, the black lines in that spectrograph, and if we know what element, like it's helium or hydrogen, the resting position on that spectrum, we will just subtract that from the observed position of that specific element in the spectrography of that galaxy, and we'll figure out its redshift and spectrography. Like by spectrography, we can find out what elements is the galaxy made up of, and that is how we can find out how far a galaxy is and its velocity. So galaxies move farther from us. uh, they are accelerating away from us at a faster rate, and as you can see in the picture, when something gets close to it, it's blue shifted, and when something tries to go far from us, it's red shifted. The age of galaxies. So ladies and gentlemen, do you have any questions? Saksham, Aryan, do you have any questions? Okay. Okay, so the age of galaxies. The age of the galaxies can be estimated by studying its oldest star population. The stellar population age provide clues about when the galaxies formed. Cosmological models also help determine the universe's age, setting an upper limit for galaxy ages. So what we do is that we have like there's a certain cluster of stars in a galaxy. We can just look at that and we'll figure out the oldest star, and that will give us a minimum cutoff. So that would be the minimum age of that galaxy. So we just get a rough starting, and the most of the old stars are main sequence stars and red dwarfs and white dwarfs. By studying those, we can get the minimum age of a galaxy. Okay, determining the age of the universe. The age of the universe is estimated at about 13.8 billion years based on cosmic microwave background information data. Observations from space missions like Planck have refined these measurements. Knowing the universe's age help estimate the formation time of its constituent. galaxies. So uh, our galaxy is about also about the same age. It was formed about 1 or 1.2 billion years after that. I just can't remember the whole date. I think so 11 or something like that billion years old. And our galaxy was formed is that by when a lot of yes, Saksham, you wanted to say something. Your voice is not coming. Your voice just starts to deteriorate after some time. So can you just rejoin again, those section? Okay. So what was I saying is that a lot when a lot of matter and dark matter formed in one space, what happened that there was a ball and then it started rotating, which flattened out the spiral arms and started to rotate and the galaxy formation and our galaxy has gotten hit by another dwarf galaxy and the reason uh, okay there's few specific things that we know that our galaxy got hit. So uh, uh, Sarvesh, can you think of ways to know that if a galaxies gets if a galaxy had collided before, how would we know that, Sarvesh? Let's
Different star populations that our galaxy couldn't have, or maybe stars that are older than our estimated age, or something like that.
Okay, so that can be one of the reasons. So are there any other reasons which we may find?
Analyzing trajectories of different stars to identify how they moved and whether there were any collisions before, maybe.
Okay, you are right. So there's that dwarf galaxy was named Gia, and we found few specific stars going in different, like their orbitals and velocities were different than our specific or average stars. They were moving in few different directions, and we named that trajectory the Gia sausage. And by that, we figured out that our galaxy collided with another galaxy when it was young, which made a lot of stars. And that it was in dwarf galaxy. Many scientists predict. So Saksham, I think so you were trying to say something. Hello, Saksham. Saksham, are you here? Okay, I don't think so. So I think so. Saksham, you were trying to say something.
Yes, Aryan, my voice is not going properly, so I am typing it.
Okay, okay. Okay, so let's just get to the topic: estimating galaxy ages within clusters. Global clusters within galaxies are among. Okay, my question was that how do we know that a specific galaxy could have been hit by another galaxy in the past? So that was my question. So let's get to the topic. Global clusters within galaxies are among the oldest stellar populations. Their color, magnitude reveal their ages, often which are over 12 billion years. Comparing these ages across different galaxies help understand galaxy formation and timelines. So you can also use the star cluster concept in the question that I just asked is that by different types of stars that aren't specifically observed in our galaxy and their trajectories, we can figure it out that uh, if that galaxy got hit by something else in the past. Okay, CMB, cosmic microwave background radiation. The CMB is the afterglow of the Big Bang, providing a snapshot of the early universe. Analyzing the CMB helps determine the universe's age and initial conditions for galaxy formation. This data supports the Big Bang theory and model of cosmic evolution. So, will the CMB ever end? What do you think, Saksham? Hello, Saksham.
Yes.
Okay, so can you give me a reasoning of that? Why do you think that way?
You see, CME is a model of the universe. Am I
Can you
audible?
just rejoin again? Rejoin again and then say it. Just rejoin and try to say your answer. So, Sarvesh, what do you think? Hello, Sarvesh.
Can you repeat?
Do you think that the CMB will ever end?
Will ever what?
Will the
The
cosmic
CME
microwave background radiation ever end?
ever end? In what
Yes.
sense?
Like we are getting radiation from the birth of the universe, a lot of radiation, and just asking, would that ever end?
The radiation is the afterglow of the Big Bang. Like
Yes.
it's just there. I don't think it will end. Can it? I'm
Okay,
not sure.
so like, would we have received all that radiation in the far future?
I mean, if entropy takes over and it all becomes like normalized, I'm not sure. Okay.
Okay, so I also don't know the answer. I think so. It's more of a more like and logical type question, because what happens is that the universe is also expanding. The space between uh, two things is getting more and more, and that too faster and faster. So that in the far future there may be this phenomena can take place, and the difference, the expansion between the universe would be so great that the photons, uh, they are traveling at the speed of light, but that may not be enough to reach us. So, Aryan, you have raised your hand.
I think I may know the answer.
Okay, what's the answer then?
It will end up in it will end because if anything has a starting, then it also has a end.
Okay,
And according to physics, there is nothing which can go forever without anything.
okay. So, we are just talking about photons. Uh, if they can exist forever if they do not get absorbed in something else. So, if a photon is lucky, may it may live very long, and after that it will may get absorbed. So that may be the case, and if it can live forever, in my sense, if it does not interact with something else.
It can get redshifted. It can keep. It's
Yeah.
already microwave, and it can keep getting redshifted until it does not even have a wavelength at some point.
Okay, that's okay. So
Like in the far, far
I
future.
so
Yes.
that's so I do not know where does this violation, how big can the violation get. So what, like, if you know general relativity, what happens is that they needed an specific conservation of law, that equation they wanted to get, but they didn't get it. And there's a lady, Emmy Noether, and which uh, proved that he gave an equation and she proved it wrong. And in case of doing that, what she proved is that an photon traveling to us uh, would lose energy due to the and so it's in clear violation of the conservation of energy. So energy is not conserved universally, but I don't but I I don't think so. It would get that far that the photon just disappears. So, Sarvesh, what do you want to say on this?
I wrote an article on this topic that energy isn't universally conserved. So, like, what the thing is that Emmy Noether formulated different symmetries that the universe must uphold for conservation laws to be there. Like, you have
Yes.
uh,
The
this
IT, yes,
time
like
translation symmetry, and it's
yes,
corresponded with energy conservation. Rotational symmetry, it's with angular momentum, and on and on. And
yes,
but these symmetries are only upholded in a static universe, a Minkowski space. But the thing is that our universe is day sitter, is expanding, positive cosmological constant, and so these symmetries are not upholded. Therefore, the conservation laws are also not globally there. They are conserved on flat enough patches of space-time, but if it's visibly curved or not linear, it's not conserved.
okay. So, do you know that I just also did a presentation on that topic. You can watch it on my channel later. So yes, the time translations and stuff. So what happened that in the equation he used pseudo tensors, and which meant that like if I had one triangle of a specific area and I change the units, like the one gets into two, like the one block turns into two blocks, but its specific area would still be same. But in pseudo tensors what happens is that the the energy of that specific thing does not remain same. So that was the problem uh, with his equation. So she proved it wrong, and in doing so she proved that energy is not conserved universally on a global scale. So would uh, that photon disappear completely if it got enough time? That's the question. Hello, Sarvesh.
I'm not sure. Over here, this just reaches metaphysics at this point.
Yes, it's more.
What would happen?
Yep. I think so. It's also a little bit on the philosophical side. That if it
Yeah,
got enough time,
metaphysics.
would that just disappear? So I like this. My feelings are telling me that it if the energy of that specific photons. Have you heard about virtual photons? Hello, Sarvesh.
Yes.
They after some time, what happens is that they disappear. They were disturbance distortion in the space time, and what happens is that after some times they flatten out, and uh, this can happen. This may be the case for the photons as well, not the virtual photons. So maybe if time is given to them, they may be disappear. So, Saksham, are you here? Uh,
What happens if it keeps on getting redshifted and until at a point it does not have a wavelength? What happens then?
it, yes, that's the thing I'm telling you. Maybe it will get flattened out in the space time, and it will just disappear. Maybe uh, I
All right.
that's just a guess. So, what do you think? Do we okay? But what I think is that it can be true because uh, the the photon will get so flattened out. It will perfectly align with the space time around itself, so that maybe will disappear. Has the energy disappeared into nothing of that specific photon? So okay, so she is not here. So, Sarvesh, you also mentioned entropy. So, do you know about entropy a lot?
Yes, yes, I've written an article on that as well.
Okay, so can you just share it in the chat? I'll just check it out.
Sure.
Okay, so I also did a presentation on that entropy topic. It's really a fascinating uh, uh, branch of science. So, uh, are you uh, are you interested in black hole entropies? Like, I think so. The whole topic of entropy is based on black hole entropy. The main attraction of entropy is just black holes. So, are you interested
Yes.
in that? Okay.
Yep.
Yes.
So, so can so there were a few things like the the laws that say that if two black holes merge, the event horizon area would be bigger than uh, the parent black holes combined. So uh, is that? I don't think so. That was it. Yeah, that entropy stuff. If two black holes combined, the product of the product black hole would have more entropy than the parent one. So uh, it still uh, grind my gears. So what do you think about that? Is that
Yeah, it
Sarvesh? Have
will
you?
be quite interesting.
Yep. So Sarvesh, what are your views on that?
Sorry, can you repeat the question? I was typing that thing out, about entropy.
So my question was, when two black holes uh, merge, the product black hole would have greater entropy than both of them combined. So I just wanted to get your opinion on that.
I mean, normally thinking it should have, right? Like, entropy is based on the surface area of the black hole, and then if the surface area increases, then so does the entropy, right?
But the total entropy they've added that entropy, and that has been increased. And if the event horizon increased, it would have increased by amount like which was similar to those of the parents one. So how would the entropy be more than their combined? I still I know that this is true, but still I did not get that much. So like uh, mass is proportional. Mass squared is proportional to entropy. So if the mass is 10, the entropy is 100 units. And if two combine, what happens is that they lose 5% in the merger process, and they're adding if we just add them, the entropy is 200, and the product is 19 solar masses units. And if you get that entropy, what would happen? It's 361, which is 161 units more than the black hole. So still I did not like we just proved it mathematically, but we still I have not do not have the intuition of that. So, just can you shed some light on this topic, Hello, Sarvesh?
Yes.
So, do you have the intuition? Like, can you give me the intuition on this topic? How is their entropy more than combined than their parent black holes combined?
I'm not sure. I haven't exactly read much about black hole physics, but
Okay.
um, I've written about entropy in general.
So, like, have you gotten into the holographic principle of black holes? There,
Uh, yes, ADS/CFT.
yep. So, you would also have seen the Bekenstein formula, right? Bekenstein formula for the black holes of black hole entropy, right? Have you heard about it?
Yes,
So I just had a question where if a black hole starts rotating, would you mean that it starts rotating and let's assume that it has a charge. The real ones do not. They regressively just pull out their charge out from themselves. But what would be, let's just assume that the thing they are, and it's specifically stated like the black hole is equal to the Bekenstein's bound, like the specific entropy packing density. So if that's the case, wouldn't that a rotating black hole would have lesser and would not reach Bekenstein's bound?
I'm not sure at this point. I'm aware of the equation, I have seen it, I've heard of it, but I haven't dug deep in it.
Okay, so
I'm not sure
would,
of the specific terms and what is in it.
uh, can you repeat? Uh,
I'm not sure. I've heard of the equation, I've seen it, but I'm not sure of exactly what's there in it, what terms are there in the equation and all. I'm not sure of that.
okay, so let me just tell you. Uh, I think so. Uh, Let me just it's KB, the Boltzmann constant, times the area divided by 4 times Planck area. So it says that one bit of information can be written at four blank pages. So, like this is the equation for K, the Boltzmann constant times area divided by 4 times gravitational Planck area. So that's the equation, and I think so. If so that's the equation, and if you just if you just want to expand the equation, the most of the part is just in constant, and there's the 8 pi m squared, which if the pi is also in constant and 8, so it's related that it says that entropy is proportional to mass squared. So that's where we get the proportionality from. So that is in the equation. So would that rotating black hole does not reach Bekenstein's bound? So I just described the equation. So what do you think? Okay, a hologram. So Sarvesh, what do you think about that?
Bro, look, I don't, I'm not sure of the exact relations in the equations. Even though I outlined it, I'll still have to, delve deeper into it to be able to answer the question. I'm not sure,
Okay.
basically.
So what do I think of it is that it's in it's the packing limit of something. If I have a room with 100 compartments, there would be only 100 people fitting in there. But what do I think of it? Even that a black hole, a rotating black hole, would still be at an uh, Bekenstein bounds because the room's compartment has been halved. So it means that only half people would be there. So it's still at its peak. So that is what I think of it. So I think so. We'll just talk about it later. Just let's just finish the presentation. So, galaxy evolution over time. Galaxies evolve through processes like star formation, mergers, and interactions. Observations of distant and thus young galaxies show different features than nearby ones. Studying this evolution helps understand how the Milky Way and the other galaxies are formed. The role of dark matter in galaxy formation. Dark matter provides the gravitational scaffolding for galaxy formation. It influences the distribution of and growth of visible matter in galaxies. Simulating dark matter observe galaxy structures more accurately. Galaxies merger and interaction processes. Galaxies grow and change through mergers and other galaxies. These interactions can trigger new star formation and alter a galaxy morphology. evidences of past merger is still visible in galaxy chaos and tidal streams. So let me just give you a quick summary of these slides. Uh, what they are trying to say is that heavier galaxies become more stable than become stable faster than younger ones, smaller ones, because there are more there's more mass to stabilize it, to get hold of those supernovas and gas clouds. So that is why bigger galaxies tend to be stable more. Summary of key points: galaxies, including the Milky Way, formed from primordial fluctuations in the early universe. We find galaxies using advanced telescopic observations across multiple wavelengths. Their ages are determined through stellar population analysis and cosmic background measurements. So, are there any questions, Sarvesh and Bhavya? Okay, I don't think so. So, yep, yes, we are done with the presentation. So, thank you everyone for joining us. So, if there are any questions, we can just talk about them. Hello, Sarvesh, are you here?
Yes.
So, did you like the presentation?
To be honest, it was very insightful, and most of the things even I didn't know about it. So, like, I'm very inspired from this.
Okay. So, let me tell you that I am also very interested in the topic of entropy. So, I just thought of adding an entropy part in the later sections of the presentation, but I just forgot about it. So I've also made an presentation on that. It's on my YouTube channel. Okay. So okay, I'll just get through it.
Yeah.
So does it contain any maths? I don't see any maths.
No, it doesn't. The previous one, the holographic principle has,
Yes, yes.
but
That one.
one.
Boltzmann constants time area divided by 4 times. Yep, I see that. Okay. So I'll just go through them.
Sure. And what do you think? Do you want to join the group I told about, the collision
Yep,
of
I'll
worlds?
join that. It just
It would be very useful to have a speaker like you on our side, you know?
okay. I'm not uh, like you're saying that I am very experienced. I haven't. I'm still a kid. I do not have that amount of experience. As you can see, uh, there are first still some flaws.
Yes, true. But, even you could reach a bigger audience, and even we could expand our reach through events like this.
Yeah.
It
So,
would
are
be
you
mutually
founder of
helpful.
this group? Are you the founder of that specific channel?
Yeah. Yes.
Okay. Okay. So I'll just join it and tell you. You can also join my WhatsApp group.
Yes, I did.
We
I did. I did.
Okay, we do these types of classes every Sunday at 4 p.m. India. So we just talk
Yeah.
about different things, and I'll just see if you want that I can make a presentation about entropy in the next class. Would you like that?
Yes, it would be very useful to be honest because you mentioned some equations and all, but I'm not sure about it. I
Okay.
could learn about it. Yeah.
So I also wanted to do that topic again because not many people joined and they weren't as many questions as I expected in that presentation. So I'll just redo that. So you can also join that one presentation. I'll just do it next Sunday on 12. I think so, 12 July.
Yes. I'll try to join, but I can't be certain. Okay.
Okay, okay. So if you can't join, you can just look that in my what YouTube
Yeah.
channel. Okay.
Sure.
Sure. I think so. It's time. It's time. it's almost time. Yep, we are 15 minutes overboard. So thank you everyone for joining us, and I think so we should leave at this point. Okay.
Sure.
Yep.
Okay, thank you so much, everyone, to joining these sessions. Uh, and Sarvesh ji, you are joined from the UAE, na? Hello.
Yes. Uh, yes,
Okay.
yes.
Okay, so actually, Aryan is very younger. I have earlier talked with them, so you can guide him. Don't without any hesitation.
Sure. But like to be honest, I'm just in grade 10 and even I'm looking forward to expand my knowledge and I'm also very young, just like him, but like I
But
also want to learn a lot
but
more.
you are studying in 10th grade. Which grade?
Yeah, grade 10. Grade 10, 10th
At the
grade.
grade. But he is studying 8.
Still, apparently he has more knowledge about it than me,